Hello everyone and welcome. Today I'll talk about linear regression with respect to normal equation and gradient descent. It's a very important and exciting topic. So let's get started. First of all, let's look at normal equation and its derivation. On the left hand side, we have y hat equals to x times theta. X is a matrix of dimensions of m by n, where m is the number of subjects and n is the number of features or the number of independent variables. In contrast, theta is a vector of dimensions of n by 1. It's the regression coefficients. To obtain estimate for theta, let's solve the equation y hat equals to x times theta using linear algebra. First of all, we multiply both sides by x transpose. The reason is because the matrix X has dimensions of m by n, is usually a non-square matrix, and does not have an inverse. In contrast, X transpose X is a n by n square matrix and may have an inverse. And this gives us the equation x transpose times y equals to x transpose x times theta. Next, to make this x transpose x an identity matrix, we multiply both sides by x transpose x inverse. So on the left hand side, we have x transpose x inverse times x transpose times y. And on the right hand side, we have identity matrix times theta, which equals to theta. And this final equation is known as the normal equation. And this equation is the same solution as using these squares as well. For full derivation based on minimizing a least square cost function, please feel free to look up the other web pages. For example, here are two recommendations. Although the normal equation is very elegant and can handle a large number of independent variables, it does not come without any problems. Here are two known problems with normal equation. First, x transpose x is an n by n matrix, and solving its inverse may involve time complexity of O(n) cubed. And when there is a large number of features, this inverse operation may be computationally very expensive. Second, occasionally x transpose x may be non-invertible. For example, when we have redundant features or multicollinearity and some columns are linearly dependent. This will make the matrix singular and thus non-invertible. Another example is when we have too many features for the amount of data we have. That is, m is less than n. Nonetheless, the normal equation is surely very useful. Typically, the matrix x transpose x is invertible. It is particularly useful when the number of features is small. With that in mind, let's look at how normal equation can be used in practice to estimate the regression coefficients. The most important line of code is this line: x transpose x inverse times x transpose times y. By using normal equation, we can estimate the regression coefficients. Here, we use normal equation to estimate the regression coefficients in a marketing dataset with y equals to sales. and features equals to the advertising budget in thousands of dollars using Facebook or YouTube. Please feel free to pause the video to read the information here in some more details. To overcome the problems of normal equation, we have gradient descent. We're going to describe two key terms first: loss function and cost function. Loss function is to quantify the difference or error between the predicted value and the actual value during the machine learning training phase. For a single training example, cost function is to average the loss function over an entire training set, and when it's done, it's considered one training epoch. Cost function is denoted by J of theta. For linear regression, it is the mean squared error. Now, our goal is to find theta, or the regression coefficients, that minimize the cost function J of theta globally. How do we do that? We use the gradient or the slope of J of theta with respect to theta to find the direction of fastest decrease. With the help of calculus, we have the gradient as the partial derivative of J of theta with respect to theta as in here. We can plot J of theta versus theta if theta is one dimension here on a graph. Here you can see that the red curve is J of theta, and this blue line is the gradient. To find the theta that will give us the global minimum of J of theta, we use this equation where theta equals to theta minus alpha times the gradient, and alpha is the learning rate. Importantly, for linear regression, this J of theta is convex, making it possible to use this equation to find the global minimum. If the curve is non-convex, then this equation is not guaranteed to find the global minimum. While the idea of gradient descent is very straightforward, there are some nuances of how it can be used in practice. Here, I will review some of them. First, with respect to the training sample size, we have the batch gradient descent, stochastic gradient descent, and mini-batch gradient descent. Batch gradient descent is to go through all samples in the training set to update theta at each iteration. In contrast, stochastic gradient descent is to use only one sample at each iteration, and that one sample is picked from an order that's determined randomly before the for loop. Finally, mini-batch gradient descent is to go through n samples at each iteration, and the number of n is between 1 and all samples in the training set. Next, we ask the question, what initial theta values can we use to speed up the minimization? Because the natural units of all the variables may vary a lot in linear regression, we go with standardized regression coefficients first, as it has the unit of one standard deviation. Here we initialize the theta with random values between -1 and +1, which are usually reasonable. Finally, we convert the standardized regression coefficient to unstandardized regression coefficients as needed. When we standardize all the variables to have a unit of one standard deviation, that unitless property also makes it possible for us to use a consistent value of alpha, such as 0.1, across many datasets. Now that we have covered what gradient descent is conceptually, let's look at how it's implemented in practice. Here, we have y hat equals to x times theta. We have cost function j of theta as the mean square error. We have the gradient as the partial derivative of j of theta with respect to theta. And then, as you can see here, we use the batch gradient descent to update theta after we go through the whole training set at each iteration. Initially, we standardize all the variables. This allows us to initialize theta to be randomly between -1 and +1. This also allows us to use a consistent value for the learning rate, such as 0.1. Finally, we convert the standardized regression coefficient back to unstandardized regression coefficient as needed. Now, let's apply the code we just mentioned to a marketing dataset where Y is the sales and X is the advertising budgets in thousands of dollars using Facebook. As you can see on the left-hand side, the green dots are the raw data and the red line is the regression line. Theta, or the regression coefficients, were initialized to be random values between -1 and +1. Therefore, initially, the fitting was not that good. But as you can see on the right-hand side, as we have more training epochs, the cost function drops rapidly. Here, we use the learning rate equals to 0.01. In practice, you may use a different number like 0.1 for faster learning. Here, we pick this number in order to show you in an animation how this learning is taking place. So here we go. As you can see, as we have more training epoch, the regression line fits a lot better to the green dots. And finally, we have this red line as the fitted regression line. And that's all for this video. In this video, we have covered two important topics: normal equation and gradient descent. And these topics are important initial building blocks for more advanced machine learning concepts, which I will describe more in the future. Please feel free to subscribe for more videos. And I hope you find this video to be useful. Hope to see you next time soon, and goodbye.